The topic of my thesis is security system based on object tracking by video stream. The aim of this thesis is to develop an object detection system capable of monitoring specific objects and notifying the owner if any unauthorized action is detected. The objects can include items such as guitars, vehicles, tools, and similar items. The object detection system should be able to locate the items within a frame and assign a class label to it. For a security system, it's essential to provide a fast response to such events. Therefore, the object detection system should deliver high performance on a CPU to process real-time video streams from CCTV cameras. Processing on the CPU reduces the hardware requirements and allows the system to be used more widely. Additionally, the model should be accurate enough to perform well under varying conditions, such as changing angles, lighting, and backgrounds. It's also important to ensure that the system functions correctly even without an internet connection. One of the early methods of object detection was the histogram of oriented gradients. The algorithm divides the image into small connected regions, called cells, and calculates histogram of gradient directions for each of them. The resulting descriptors are classified using support vector machines. Thus, the algorithm outputs a segment and predicts the class of the tracked objects. However, for real-time object tracking, this method consumes too many computing resources and has low accuracy. The next method for object detection is region-based convolutional neural networks. The method attempts to identify regions that potentially contain objects using algorithms like selective search or edge boxes. Then it extracts features such as edges, textures, or shapes from each region using convolutional neural networks. As in the previous method, the classification task is solved by SVM. This method provides high accuracy but also has significant drawbacks. Specifically, it operates slowly due to several complex stages of image processing and overlapping regions, which can lead to the identification of unnecessary objects. To address the main drawbacks, namely the complexity of the RCNN operation, the faster RCNN algorithm was developed. The algorithm for dividing the image into the regions was replaced by a regional proposal network, which reduced the number of potential regions and optimized the analysis. As a result, the accuracy and performance of the model have increased, which already allows this model to be used for real-time operation. You Only Look Once is a state-of-art object detection system which is still actively developing and improving. YOLA divides each image into cells. Several rectangles are selected around the cell to define the object. Intersection over union is calculated for each cell. Detected objects with low intersection over union considered as containing no objects. For each bounding box, confidence score is calculated. Convolutional layer returns probability of object's class, which multiplies with intersection over union. Predictions with low confidence are filtering. At this step, some overlapping box is still presented, but one is selected by non-max suppression algorithm. This technology allows to analyze images in real time with high frame rate at high resolution of the images. RCNN and faster RCNN models process low amount of frames per second on same dataset. YOLA analyzes more than 30 frames per second with higher accuracy. Large language models such as ChatGPT have been actively developed. They are capable of performing many tasks but are limited to text input and output. To solve this problem, vision language models were developed. Florence 2 is a lightweight VLM open source by Microsoft. It has object detection functionality, so it can be used as a part of security system. The training data should include images task problems. For object detection, data should also include labels and box locations. The aim for the detection model is to locate guitar with mark which simulated unique object with tracking requirement. RoboFlow's universe contains sets of images with guitars, but for this work is especially suitable dataset with guitar of different types, where types are labeled for each image. Selected dataset has 1000 47 annotated images, and 21 classes. An additional 36 images of guitar labeled important guitar were added to this dataset. The photos were taken from different angles, in different lighting conditions, and from different distances. The additional images were manually annotated using RoboFlow's built-in tools. After that, a version with augmented images were generated, where the angle, brightness, and blur randomly change for better performance on the security system in different conditions. Augmentation increases train set in 3 times. Since important guitar is a mass-produced at the factory, this guitar has marked using a patch to simulate a unique object. Additional 73 photos of the marked guitar were taken. More images were made so that the model could better separate the two versions of different guitars. These images were labeled as important guitar marked manually as well and added to the dataset. Augmented version and division into train, test, and validation set were made. A platform with NVIDIA L4 GPU with 22 GB of VRAM was used for training. 6 YOLO models were trained for this work. YOLO V8X on the dataset with augmentation but without marked guitar class, other models included. The total training time was 4.5 hours. YOLO V8X on the dataset with augmentation, the total training time was 5.6 hours. YOLO V8M on the dataset with and without augmentation. This dataset contains only important guitar and important guitar mark classes. The total training time was 0.3 hours in both cases, but it takes less amount of epochs for augmented version. YOLO V10L on the dataset with augmentation. The total training time was 4.9 hours. YOLO V10M on the dataset without augmentation. The total training time was 1.8 hours. Training stops after 100 epochs without important loss changes. The model obtains 100 epochs ago are selected. Transfer learning was used to train this model. It differs from conventional learning in that the model being trained has already been trained to recognize certain classes, and the next training will allow this model to begin to identify new classes. In the case of Lawrence 2, the model comes pre-trained and identifies all guitars as a class guitar. However, the dataset requires not only identifying a guitar, but also determine its type. To achieve this, the model needs additional training. The training took 60 epochs without early stopping. Unlike YOLO, this model takes much longer to train and consumes about 20 GB of VRAM, while the previous described model used less than 12 GB on the same dataset with larger batch size. Before training, the model was able to recognize a certain set of objects in photograph, but after additional training, the model stopped identifying the classes that could identify before. YOLO V8X model trained on the dataset with augmentation and without marked class was able to distinguish important guitar from other types of guitars, despite the low number of examples in this class. The result was achieved due to the augmentation process and the high quality of examples, which captures various conditions and angles. Also, YOLO V8X model, when trained on the dataset with augmentation and marked class examples, is capable of accurately distinguishing between important guitar marked, and other types. The important guitar marked category contains a large number of examples, which is sufficient to train the model efficiently. Also, YOLO V8M with two classes provides a mean average precision of over 0.25 for both classes. It's not capable of ensuring high security system quality, because other types of guitars are also incorrectly marked as important guitar marked. To successfully distinguish different guitars from the marked ones, the model should be trained on examples that include other types of guitars. The previous models has a vulnerability with hiding marking patch by hand, so examples where this mark is hidden were labeled as guitars without mark, added to the dataset and processed by YOLO V10 models, so the additional examples resolved the issue. YOLO V10 model both provides mean average precision metric at 0.81 level. Lawrence 2 model are capable to detect marked guitar, but it has mean average precision at 0.35 after 7 hours of training, and non-marked guitar are classified as marked in most of the cases. This model has complex architecture and consumes more calculation resources, providing 1 frame per second in real-time image processing. Models were tested on a laptop with an Intel i5 Comet Lake processor, and the best results were provided by Yola V8M and Yola V10M, which were able to maintain the operation of the object tracking system at 30 fps. The patch simulated a specific unique detail, but instead of a patch, the object may have signs of wear that needs to be compared with a new one. So, the model can more accurately distinguish between a new and a unique object. Additionally, for better accuracy, it's important to train the model on different types of the object rather than just using two classes, with and without marking, since, in the case of guitars, electric guitars were mistakenly recognized as marked. Based on the trained models, it's possible to create security system for object tracking using a video stream. Each frame is extracted from the video stream and sent to the model for analysis. If the model detects a target class, a bounding box is drawn around the object, ensuring that the required class is contained within it. Thank you for your attention.